Okay. So, I was asked a question about, which is an interesting question about how sort of modeling we've been learning this semester could be applied to water resources area. And without planning to dominate the entire class with this one question, I thought it's a neat question to bring us into a glimpse at a topic we haven't really talked about, which is hybrid methods. So when we think about water resources, we're talking about systems that are often sort of combine natural elements. So you have hills and catchment basins associated with water. Water kind of flows down perhaps into these reservoirs, right? And it collects, and from then it may drain into other components. And there may be canals which take from reservoirs and bring that water elsewhere, right? So they bring the water to farms or to industry, like that. So there may be factories which produce output, and there may be houses, right, with families living in them, which make use of the water as well. And may be used for farms as well. And so you have a variety of uses of water. These are broccoli stalks. Okay, but you can map them to your plant of choice. When we think about a system like this, a water resources system, there's many angles to it, which a first glance will often omit. It's a system that combines natural elements, for sure. Much of what we're interested in for many water resource questions concerns catchment basins whose landforms are natural. They're not things we've imposed. They're not inherently engineered. They're natural landforms, natural depressions where water gathered, natural regions of uplift, and areas with harder rock that prevents permeability and leads water to flow. So there's many natural elements associated with the system. Rainfall patterns itself are natural by nature, right? They're systems that we can only very indirectly affect. So there's a lot of natural elements in this. And natural governing, it's not just elements, it's governing processes. So natural governing processes. What I mean by that is the things that shape much of what we deal with water are given to us. We don't have a chance to sort of change them. It's monsoon seasons, or it's aspects of the evaporation cycle, or aspects of freezing and thawing that we can't change, even though you might want to sometimes change thawing and freezing. So there's natural elements. There's technical elements as well, and processes. So I would include here, and this is a crude term for it, but I'd include things like locks or aqueducts. There's engineered reservoirs and dams, variety of other elements, right? These are sort of engineered structures. These aren't all of them, though. There's actually many others that may not have been built. These are all notable because they're built for the water system. but there's many others as well that are not per se built for the water system but effective. Examples would be things like impervious surface area associated with cities, right? So when we have a city like Saskatoon or a city like Los Angeles, even more so, there's large amounts of paved areas. And those paved areas have big impact on water flows because they lead the water to flow off very quickly when there's rainfall, right? Los Angeles, you can get much of the year very little rainfall, and then you get rains coming down, say during the Santa Anas or what have you, and large amounts of water then sweep down the streets and the available sidewalks and so on, and you get a first flush effect where it flushes all these pollutants and so on into the ocean. And so there's impervious surface area associated with cities and built areas. So this is sort of cities and built structures. So roads, structures, so roads, etc., roadways, and causeways of various sorts. So there's a whole lot of technical elements. These are fundamentally engineered systems. These are, the first ones are sort of natural systems. The final one is one that's very easy to omit, very easy to overlook, and that's the social elements of it. I'm going to call it social. What you sometimes hear the term is socio-technical systems. So there's groups who will talk about they study socio-technical systems, meaning they sort of cross the boundary here. And this may seem like a side issue. It may not seem as fundamental as the natural or the engineered system, but it is just as fundamental, even if it's oft overlooked. And this has to do with things like the industries involved, the various types of industry, balance of industries, the level of water intensity associated with those sort of types of industries. There's attitudes towards conservation, conservation sort of initiatives associated with this. But there's also aspects of sort of people's responses to pricing, right? Pricing water leads people to change consumption patterns. There's issues having to do with, in really water shortage areas, there's things like hoarding effects. So if people are anticipating water not being available, they may take a lot more up front, and that leads to even less being available, and you get this sort of vicious cycle associated with that sort of pricing phenomena. There's also sort of just patterns associated with day-to-day water use patterns, I'll say. So certain types of households will have certain types of patterns in terms of use of water. Now, the deal is that when we're thinking about a system, we've got to understand what question we're trying to address, because different questions within the water area, the water resources area, will cross these three areas to different degrees. So some will have to do, for example, with the impact of industry on water. And here, pricing might be a big factor, because if you price water at a level for industry that will lead it to be valuable, you may get less wasteful industry in place. Similarly, if you're dealing predominantly with design of catchment basins, it may be that the social elements aren't as prominent as the technical and the natural elements. The engineered components of designing the reservoir, and the elements associated with the elements associated with the sort of natural systems involved. If you're trying to deal with conflict between different groups, like in California, there's a lot of concerns about conflict between the agriculture on the one hand and domestic use. That if that's a big concern, the social side really comes out in a big way. Okay, so I'm not going to go into details about your particular research interest. We can do that in separate discussions. But what I want to highlight is that each of these major areas has a first order effect. The time constants are somewhat different. Like natural elements may involve day-to-day variability, rainfall, the patterns associated with the level of precipitation soaking into the ground, etc. Technical elements evolve somewhat more slowly. It takes a couple of years to do a rollout of a new reservoir, what have you. Dams take even longer to build. Social systems, some of the factors there, like the balance of industry, get shaped over decades potentially. Other things like people's response to water pricing, hoarding behavior, water use patterns, these are shaped actually at a somewhat smaller time scale. So if we think about a water, one of the lessons I hope you'll come away from this course is that when we think about a system, it's important to characterize it broadly. It's important to question your boundaries. And a lot of people traditionally, if you go back 100 years ago in civil engineering, they were dealing with these first two. And it's really in the past 30 or so years, you see, particularly in civil engineering, the real appreciation of what they call systems factors, that you've got these other elements. And these elements interact. There's feedbacks between these. If you have more consumption, it leads to costs on the technical side, leads to more worries about depletion due to limitations in rainfall. And there's, of course, longer-term things like climate change, etc. So people are increasingly trying to build models that incorporate these different elements. And what sort of models do they use to build these? What sort of models do they use to try to incorporate these three elements? Well, there's two primary sorts that you see being used. And one of them is a technique known as system dynamics models, and another is a technique known as agent-based models. Okay, so what I'm saying here is actually ties in quite well to a lot of what we're talking about in the course. So the question was posed, where would agent-based modeling fit in here? I think that's kind of unpacking the question. Because you say, where does AnyLogic fit in? Well, first of all, AnyLogic supports both these sorts of modeling. So that's one place it obviously supports the requisite types of modeling. But how would you map any given one of these to these factors? Well, with system dynamics, people have built models that characterize changes in people's attitudes and consumption patterns in response to pricing. And they also use those SD models to simulate sort of the accumulation of rainfall in basins and the flow of water between different areas. The instructor in this room has actually spent quite a bit of time doing this in the water infrastructure area some years back. Using system dynamics models. However, agent-based models are of keen interest here because there are certain aspects of the situation that are characterized neatly at the agent-based level. What pieces of this would fit in to an agent-based characterization? Can anyone come forward and suggest, you don't have to physically stand up, but could anyone suggest elements of this that might be characterized using an agent sort of lens? Pricing and response to pricing. This is definitely one. People might have variability in how they respond to pricing. There's variability in income, among other things, right? So Someone with a huge income might be price inelastic with respect to, sort of small pricing changes, right? Someone with lower incomes might be more elastic, might change their consumption based more on the pricing. And you want to capture that variability in response. You might also want to capture elements of memory, history, associated with people's responses that might affect their response to pricing changes. And hoarding is another aspect, sort of if they try to save away some water just in case they're not going to be able to get some in a few days or something like that. Not a big concern in Canada, but a big concern where I've worked elsewhere. And generally sort of water use patterns on a day-to-day basis. The fact that, for example, in the context of scarcity, people can save up a certain amount of things that they would otherwise do with water for a certain amount of time. They can, for example, not run the dishwasher, right, for some days and instead wash dishes by hand, right? But another thing they could do would be to hold off washing clothes until a water emergency is passed, and but they can only do that so long. After a while, they got to do their clothes, and then you've got maybe a bigger amount of use going on. If you're dealing with industries and industry interaction or negotiation, industry representation, there's a lot of interest in having industries represented, or even particular farms or factories using agents, because there's decision making that goes on at that level. There's decision making about what to do or how to invest or how efficient to make their industrial processes or what have you with respect to water. People's response to conservation initiatives, and in fact, simulating the spread of conservation initiatives. These are all things which might depend on factors like social networks, like people's location, which you might find easier to capture in an agent-based model. The fact that this given factory is located in this place, or this given individual has these characteristics, or has this memory of past experience, or has this background. The fact that an industry has access to certain types of water-saving equipment already in place, and it might modify that, go to a reverse osmosis process if the pricing of the water is such. If you want to simulate things at that level, an agent-based articulation can be quite effective. So we have some systems here which are very well simulated with agents, if we want to do so. The spread of attitudes towards consuming water, for example. Again, that's like a spread, almost like a spread of pathogen, but it's a spread of an idea, and that's what agent-based models are often used to characterize. The spread of innovations. How do innovations spread in industry? How do innovations spread among different players? That can be simulated quite nicely using agent-based formulation. It doesn't have to be. You can do approximations in SD. They just have some trade-offs, and it's hard to get the specificity you can get with certain agent-based formulations. But how about water runoff? Are we to simulate using agents each drop of water that lands on this hill and rolls down to this basin? Is that a good use of agent-based modeling? Are we to simulate each drop of water that lands in the reservoir and that flows down here? It's more a continuous system. So there, having stocks and flows is actually quite a nice approximation, right? Having stocks and flows associated with the flow of water, quite literally, the flow of water between different areas of this system. So stocks and flows are a very natural description for what is quite limited, quite literally the plumbing of the underlying system. So how are we to bring together these two extremes? How are we to link up link up these elements to deal with this tension, but underlying the fact that for some things, an agent-based characterization is very natural. For example, the decision makers at the household level or the industry level or the farm level. It's a very natural mode of description there to have agents, but at the same time, it's very natural for other elements. The technical and the natural elements are very nicely described with system dynamics. Well, ladies and gentlemen, how are we to deal with that? The words are on the board. So we can use hybrid system science techniques for this. And it turns out that the good news here is that AnyLogic supports very readily not only models each using one of these techniques, but it actually supports single models that combine these techniques. And this is one of the most powerful uses of it. It turns out these different types of system science methods, system dynamics and agent-based modeling, are highly complementary. They seek to answer often different types of questions or different pieces of a system, and no one answer replaces the other. So I'm just going to give you a glimpse of this because we have other things to talk about today. But we found, so our group here at the university is and has for a long time been sort of a leader at looking at ways of combining these different approaches within a single model and sometimes with different models within a single project. So, I thought I had, yes, right. So there's some models that I can show you where, for example, agents within a population have stocks and flows associated with each agent. Each agent is associated with stocks, for example, representing their level of infection within them and level of uninfected cells, their viral level, so the amount of virus in them, and their response to the immune system. And each agent evolves according to these stocks and flows for certain continuous quantities, and for certain discrete quantities, they may evolve with respect to state charts, for example. Okay, turns out this can be done in VenSim. It's much nicer to be done in AnyLogic. So I have several other elements that we won't be talking about here, but oh man, but how would we do this in AnyLogic? Let's just take a look. Ladies and gentlemen, fire up your AnyLogic. Let's create a little hybrid model. Oh man, there's a picture taken. Okay, I don't know. I'm not going to be put on Instagram, am I? Okay. Okay, so we're going to create a little hybrid model which has agents and has stocks and flows. Maybe I'll reuse an existing model just to save us time. We could here go take a look at. Oh, look at that. For a stock and flow model with movement, we could put it there. But I think I'm going to. I think I'll going to put it in one that has just agents without movement. That's what I'd like to do. Minimalist network. Yeah. Okay. This is a decent one to do it in. So here we have children, for example, in some main class. And let's first run this thing so we get a sense of what's there. Here we go. So we're going to run this. Oh, there's an error. Oh, boy. Okay, method population size. Okay, fine. Okay, so what do we need to do? We need to put a statistic called population size here. So forgive me while I, case count, and then we want population size. Okay, there we go. And we want to count the number of people in the population. That's actually a pretty inefficient way to do it, but I'll do it for now. Okay. Okay. So here we have a model, and the model has agents within it, and the agents are being added and removed over time. we could have in the same model, for example, a stock and flow collection. So we could place in Maine a stock associated with, reservoir, right? And this stock would be associated with an inflow associated with, rainfall, something like that. What's that? Precipitation, thank you, yes. Because we have other types of precipitation besides rainfall in certain climates. Okay, so that's good. Assume summer, right. And then we might have an outflow associated with evaporation or something like that, right? Evaporation. And then we might have something associated with use, right? Right? Okay. So this would be sort of water household consumption, something like that. What do you think? Household consumption. Okay, household consumption. Okay, so that's a start, but we've got to take this thing and we've got to put it up to the reservoir. Okay. Let's go drag this thing down to. Hey, come on. Hey, why won't you? Hey, okay. Fine. We'll take you down here. I see. This is the handle. There we go. Okay. Now, household consumption. Maybe each person in this model, we have them called, there's children, but then there's persons. Okay, each person in this model might be associated with a consumption rate or something like that, right? Consumption rate, and right now I'll make it a parameter. Maybe in general it will be a stock and flow, or maybe it would be based on their state of some state chart. And we will have in Maine, we're going to have a distribution associated with that, associated with the consumption rate, of the population here, of maybe, maybe it's a random, yes. Household consumption, yes.
Are you giving any specific term or this demand are you giving?
Well, I could break that out in as much detail as I wanted at the household level. In other words, I could make it, right now it's a crude parameter, but you could, within the agent, you could actually make it depend on certain types of consumption, right? And those types of consumption might vary in association with season, for example. So during the summer, they use more water to water their lawn. During the winter, they don't. But maybe certain families which have installed a low flush toilet or a shower head, they would use less water. And so you could record that all at the agent, right? You could have them, if the pricing is right, they go get a low flush toilet. And now you record in a parameter associated with that agent, you record, they have a low flush toilet, and then their consumption is lower, right? And you could, and maybe after they install it, their friends are more likely to install it. So you have a social network effect there. All those things could be captured at the agent level. I'm just trying right now to show the basics of how you'd link these two types of modeling together. So maybe, for example, we have a consumption rate for each individual, which is drawn from a normal distribution with standard deviation. Gosh, I don't know the amount of water used per day per person. Does anyone remember liters?
In Saskatchewan, it's 1 or 1.5
meter. Okay, so
per day.
a cubic meter.
Cubic meter.
That's a fair bit of water. Okay, I'll just guess that. So with a standard deviation of 0.2 with a mean of 1, we'll treat it as in cubic meters. And really, I should make that clear. This is consumption rate in cubic meters per day. Okay. So we could do that, and then household consumption here would be what? How would we determine? So we have each person in the population now having a consumption rate set from a variable, and we could run this model and see people distributed as to their consumption rate, right? So here we have all these different people, and each of these members of the population has a different consumption rate, right? Again, we would want, for a real model that's looking at consumption patterns, to keep track of a lot more information, like do they have a low flush toilet? Do they have a special shower head? Do they have a dishwasher? All that sort of stuff. But you can keep track of that at an individual level. And then, ladies and gentlemen, how would we relate that to this flow? What would the value of this flow be? If that was consumption rate per day of a household, how would it relate to this flow? Anyone? We have a population. The population is drinking from the reservoir. It's using water from the reservoir. How much water goes down here per day then? Sorry? Yeah, we want to make a statistic for the population to total up the consumption rate across the population, right? Again, in cubic meters per day, which we'd want to sort of make clear. So this is in, consumption in cubic meters, cubic m per day, or maybe you say m3 per day, or what have you, right? In meter cubed per day, something like that. It'd be a sum across the population of each person in the population. What are we summing up? Population dot consumption. Hey, I think I saw a bad thing. Yeah, okay. I'll just have to remember it. Consumption rate, and this is true. It sums up over everyone in the population, right? Sorry? The condition is not needed, but, well, let's put it this way. It forces us to give a condition. So who is going to be totaled up? The sum is going to be over whom? This gives a condition. This gives a criteria by which someone will be counted. In this case, everyone is being counted, so it's always true. In general, it could be a condition that says, like, population member is an adult or something like that, right? And here, actually, I'm questioning whether the agents would be people or whether they'd be households, because you might want to have households be, hey, okay. So consumption rate, what was it called at the level of a person? It was called consumption rate, and I just, it's not called population. What am I doing? Oh, man. It's been too long a semester. Okay, so here we go. So now we just had item.consumption rate. Why item? What does item mean in that context? You can remind me? I skipped over that quick, but I want to make sure everyone, what's this? Item is the population member in turn. So we're summing up over each person in the population called item, their consumption rate, right? And we're using that to drain the reservoir. So maybe we have precipitation coming in according to some stochastic process, because rainfall is not always predictable. Eh? So maybe we have, I'll just do it as a white noise process, but maybe, it is drawn from a log normal distribution or something like that. So log normal with a log mean of, so in other words, a mu parameter of, say, 5 and a log standard deviation of 3. Okay, so now we have this precipitation coming in, and evaporation evaporation depends on how much water there is in the reservoir, right? So the amount of water that's evaporating depends on some evaporation rate, correct? So we might have a sort of evaporation rate, and maybe that will depend on, in general, maybe that will depend on so I'm going to take this out. Maybe it will depend on temperature, for example, right? Evaporation rate. In the winter, this is probably not very high. So it's evaporation rate for current time or something like that. And I'm not going to specify that in great detail here, but the point is we could hitch this up just like this, and then we can take evaporation. Maybe it's the reservoir level, reservoir times the evaporation rate for current time, something like that. Maybe this evaporation rate per current time, I don't know, maybe on a per day basis, 1% of the reservoir evaporates or something like that. That's awful steep, maybe 0.5% or something. And then we have an initial value for the reservoir of, I don't know, 1,000, 10,000 cubic meters. And then we have household consumption, which was set, we want set to what? Well, we computed a population statistic, remember that? So this was in consumption in meters cubed per day. We computed that in the population. And ladies and gentlemen, we will try to compile this, and it's exhibiting dysfunction, so pardon me for a second. Okay, so okay, so it wants double, it wants a minimum, and then, okay, fine. So 3.0, and then a minimum of 0. It can't go below 0, that's for sure. So it's it was unhappy there, and then we'll run, and here we go. Okay. Oh my gosh. Oh, what an ugly thing. Sorry, folks. Let's drag this over here so it's not clogging up our precious screen real estate. Okay, so here we go, and here's our reservoir, and here's our household consumption, and here's our precipitation, which is varying quite precipitously among different values. Let's go see. For different days, it's different amounts. Obviously, we could put in and or some other sort of model of sort of how precipitation varies. You'd want to get some covariation, because if it's rainy one day, it's more likely to be rainy the next. So having some time series model, probably an ARIMA model, would be quite nice. I've used those before for this. And so here we have rainfall coming down. Oh, it looks like we're in a dry season right now. And meanwhile, the drought has been broken. And meanwhile, we have our reservoir, and the reservoir is varying. Oh, it's going up. And we have our household consumptions, and the household consumption is going down over time, interestingly. Probably because, okay. Oh, because people are dying at faster than they're coming in. Okay. Well, this is not meant to be a perfectly accurate simulation of Saskatoon, but it does show how we could create a hybrid model that combines, on the one hand, system dynamics elements for the natural and technical elements on the one hand, with agent-based models, which could be used to capture decision-making, memory, social networks, particular positions, which might affect their consumption. Like if they're next to the canal, they use more water. If they're in rocky ground, they use less or something. I don't know. But the agents could have different consumption patterns, different price elasticities, different infrastructure in place as far as water conservation, etc. Does that answer a bit of your question? Okay. Okay, great. I know that's not of central interest to everyone, but what I hope will be the lesson is that combining model elements of different sorts in any logic, on the one hand system dynamics elements, on the other elements from agent-based modeling, it's literally as easy as dragging things in and setting them up and just putting them in a shared model. And again, don't get in a mindset where you think, state charts only can live in an agent, and stocks and flows cannot be combined with agents. No, you can. Just question your assumptions. You can have state charts in the main class. You could have stocks and flows in agents. Stocks and flows don't have to live in the main class. They can live elsewhere. So here we've seen some of the flexibility afforded to us, ladies and gentlemen, by this palette over on the right-hand side, and using it creatively to combine things. Here we have stocks flows combined with use of population statistics, as illustrated by this element here, by calling off to the population statistics, which computes things by aggregating up from the individual level. So models which combine these elements, system dynamics and agent-based modeling, quite straightforward to build in any logic. Okay, so these are